Yeah.
Okay.
Okay, so here we are.
Great.
Let me start the recording on my device as well, so that.
Yeah, totally. This way we have a backup in case.
Yeah, okay, so it should be working, yeah.
Okay, great. Okay, so let's start. So I'm very happy today to introduce Yvan Nourdin from the University of Luxembourg. So this will be a thematic session revolving around the Stein method. And the first talk is given by Yvan. We'll speak about the Breuer, oh, okay, I don't know how to pronounce it, but a major theorem and then old and new stuff about it. Please.
Thank you very much. Thank you very much, Sebastian, and thank you, Sebastian and Bastien, for this invitation. It's a real pleasure to give this talk. I'm going to give an old-fashioned talk, meaning that I will write on my tablet like a blackboard. So for this reason, and also because I would like to save my Wi-Fi, my bandwidth, I will stop my video because otherwise you just will see me writing, so it's not very interesting. Of course, also feel free to interrupt me in any case you need if something is unclear and so on. Okay, so I would like to speak about so-called Breuer-Major theorem. Of course, I don't assume that you know already what it is, so I will explain this during the talk. And I would like to present you some quite old stuff, so the beginning of this theorem, and some very new things, which are based on a joint work in progress with Leonardo Meni, who is my PhD student here in the University of Luxembourg. And okay, so the idea, I will explain first what is the result, then I will tell you the intuition people have on this result, and then I would like to explain that we got some results which are for some people against the intuition, and so I will explain. Okay, so to start with, let me fix for all the talk a dimension, an ambient dimension. So I will work on RD, and I assume that just D is bigger than 2. And I will write, like usual, this way the Euclidean norm on RD. Okay, and the quantity I am interested in this talk is the following. So I will call it YT during all the talk. So I define it like integral for x in the ball centered at 0 and radius at most t, phi of bx dx. So let me put like this to say that this is the important quantity here. And now I explain what is phi and what is b. So phi here is my first ingredient. This is a continuous function from R to R. So I assume it is continuous just to be on the safe side with respect to the integral. Most importantly, I assume that this is square integrable with respect to the standard Gaussian variable. So here, when I write n, it means the standard Gaussian. And it's not really an assumption, but just to simplify the statements, I will assume that the expectation of phi of n is 0, so that phi of n is centered. Otherwise, you just have to subtract by this guy. And my second ingredient, so it is a bx. So bx, this is a collection of n01 random variables indexed by x in Rd. And so more precisely, I will assume that this is a Gaussian field. Also, I assume that it has continuous paths, just to be sure that everything is well defined. I will assume also for simplicity that it is centered. And so, as I said, a collection of n01 variables, so it has unit variance. And more importantly, I will assume that it is stationary. So in this context, because it is Gaussian, it just means, and because it is centered, that the expectation of bx, by is a function only depending on x minus y. So for some c, from RD to R. And the fact that I am assuming that also the BX are standard Gaussian just is a consequence of the fact that C0 is 1. Okay, so this is a context. I will just give you an example of such a quantity with explicit phi and explicit BX in a minute. But this is something, this kind of functional, which arises in a lot of situations. And you will see in the forthcoming talk by Giovanni later a situation also where we have this kind of function. So for the moment, I don't speak too much about the relevance of this, but as you see, this is quite general. So there are many situations where you have to deal with this guy. And so my problem for this talk is the following. So I would like to know when I divide YT by its standard deviation, if I can say something about the limited law of YT divided by its standard deviation. So for instance, it could be Gaussian, but we will see also other possible limit during the talk. Okay, so to give you an example, so let me just recall that YT is integral for x less than t of phi of bx dx. Okay, and an example of situations where we can be interested in studying the limit of this object could be the following. So imagine your bx is not fractional point motion because it is not stationary, but the process of increments of the fractional point motion, zx plus 1 minus zx. So where z is a fractional point motion, that is the expectation of zx zy would be 1/2 norm of x power 2h plus norm of y power 2h minus norm of x minus y power 2h. So this bx defines this way, defines stationary Gaussian fields on third variance 1 and all the assumptions I need. So here h is a real number between 0 and 1 called the Hurst index. And so this is a popular object in probability theory, and there are many people using it to model phenomenon. And for instance, if you are a statistician, you observe B and you would like to estimate H from the observation. So YT is something that you can observe, and for phi you could take, for instance, the P variation. So U absolute value of U power P minus expectation on n power P to make it centered for P bigger than 1. So for instance, for P equals 2. And starting from this, it's possible then to construct an estimator of H, and then if you want to construct confidence intervals and so to have an idea on second order results, you are interested in the fluctuations of YT divided by its variance. Okay, so it's just an example. You will see other examples during the talk and in the talk by Giovanni. And now let me say something. So let me state the Breuer-Major theorem. So it's a result which dates back to the 80s, so 40 years ago, more or less. And so now I'm going to explain the old part of my title, old and new. So I'm just going to explain what is the Breuer-Major theorem, which dates back again from the 80s. So in order to state it and in order to say something about the fluctuations of YT, limit theorem when I divide YT by its standard deviation, a crucial object is the so-called Hermit Rank of Phi, so which plays a crucial role in the study of the possible limits for YT. So let me remind you what is the Hermit rank. So my function phi, if you remember, I assume it to be square integrable with respect to the standard Gaussian. And so I can expand it in terms of Hermit polynomials, which are the orthogonal polynomials associated with the standard Gaussian distribution. So I have a sum over Q, And let me assume that this Q here, this Q here start at R, and now I have some coefficients, so AQ, HQ, so these are real numbers, and these are the Qth Hermit polynomials. And to say that the sum starts at R means that I am assuming that AR is not 0. Okay, just a remark, if you take the, if you evaluate phi at n and you take the expectation, you will get A0. So A0 is nothing but the expectation of phi of n. And because I assumed that it was centered, just for simplicity, then it means that my Hermit rank R is bigger than 1. Because here, okay, so this R is precisely the Hermit rank. Okay. Let me just do here a meta remark, so which is not a precise statement, but just to say that in practice, when you deal with function phi's coming from a given problem, in general, it is very likely that the value of R is either 1 or 2. So I mean, for the value of R to be bigger than 3, more or less it means that you did it on purpose. So because you must have A0 is 0, so we can assume it. Then we must have A1 is 0, and then A2 is 0, and so it's a lot of conditions. So in general, just to have an intuition, we have so both R is 1 and R is 2 are usual, and R is 2 is when the function phi is symmetric. So for instance, the Hermit rank of this function phi here is 2 because of the symmetry, the fact that phi of minus u is the same than phi of u. Okay, so just keep in mind that there are the two values that we deal with in general. Okay, and now let me state the Breuer-Major theorem, so which comes from the 80s and precisely 83. So this theorem is as follows. So if the function c, so I will show you again what is c, what is r, and so on. So if the function c is r integrable, so what is c? You remember that it was the covariance of b. So c is something related to my b. R is the quantity related to phi. This is the Hermit rank. So here it's this condition. When I say that C R is integrable, it's a condition both on B and phi. And under this condition, so if this C is R integrable, then it is enough without no more assumption to imply that YT divided by its standard deviation converge in law to the standard Gaussian. So it's a nice result because it's CLT. It gives you Gaussian fluctuations under an assumption which in practice is in general quite easy to check. So the fact that indeed you have that this condition is satisfied. Okay. So if C is R integrable, then you have Gaussian fluctuations. Now the natural question, and this question was also, of course, asked in the 80s already. So what happens if C is not R integrable? So of course, we can ask whether this result is some sort of if and only if or not. So it's not an if and only if result, but we have this very this celebrated result. So by Breuer and Major, so the same Major. It was published in 79 and this was in 83, but both were done more or less at the same time, and the ultimate one was published in 83, but they were results produced more or less at the same time. So if we want to get non-Gaussian limit, we have to be a bit more precise on C. So if C of x behaves at infinity like norm of x power minus beta, and we can allow also a slowly varying function. So this L, But okay, so you can think of it like a constant if you want, or a logarithm or something which is slowly varying, with beta between 0 and d over r, strictly, which if you look, this beta between 0 and d over r is exactly the range of beta we need to have that C is not R integrable. Okay, so it's a Riemann criterion. Under this assumption, you are not in the Breuer-Major case, so C is not R integrable. And in this case, what happens is that you, for the same quantity, this time you will converge to the so-called Hermit random variable. So I'm not giving you the precise definition. If you don't know what it is, just I will make some remarks. It has two parameters, an Hermit random variables. So it has an index. And so the index will be R, exactly the R, the R, which is the Hermit rank of Phi. And it has a self-similarity index, the analog of H for the fractional Brownian motion, and this H will depend, the definition will depend of the beta. So this is why we need to be more precise, not just saying that C is not R integrable. We need this precise form because the limit depends on this parameter beta. And just a thing is that Hermit random variables, except when R is 1, so for instance, when R is 2, is not Gaussian. Okay, so this is not Gaussian, except when R is 1, because in this case, this is also a standard Gaussian. Not Gaussian if R is bigger or equal than 2. Okay, so let me maybe summarize this just to show you the intuition we can have on this result. So if C of x has this form here, so like x minus beta L of x. So, okay, I could even write, I don't know why I write equivalent. The equivalent can be put in my L function. So with L slowly varying at infinity. And let me assume that R is bigger than 2, just to avoid the particular case when R is 1. Let me take here a beta strictly positive, and so and L slowly varying. Then I have two cases, more or less, according to the previous two theorems. When beta is strictly bigger than d over r, I am in the situation where this C is R integrable. So in this case, I'm going to converge to the N01 distribution. So I get Gaussian fluctuations when beta is strictly bigger than d over r. And because I choose R bigger than 2, I get that the limit is non-Gaussian in the contrary. So if beta is strictly less than d over r. Then we have the critical case, d over r, for which in general it is also Gaussian. So the intuition we can, I write it here, the intuition we can have from this summary, just I prefer to write here to have on the same sheet. So the intuition is that if we have short memory, so short memory means that C is bounded enough so that it is integrable and the condition of Breuer-Major is satisfied. So short memory in general gives Gaussian fluctuations, give rise to Gaussian fluctuations, and long memory, so which is more the de Broglie-Major result, gives rise to non-Gaussian fluctuations. Okay, and so this is the intuition most people have, including myself before I worked with Leonardo on this work. So meaning that if you give me a functional yt, you give me a function c displaying a long memory, which has and the phi you give me as an Hermit rank bigger than 2, and you ask me, do you think that the fluctuations are Gaussian or not Gaussian? I will say, okay, try to prove that they are non-Gaussian, because this is most likely, right? Because if you want to prove that they are Gaussian, we will mention Stein's methods, and we have tools, but we for this, for instance, using the tools from Stein's method, but for this, we need to know, we need to have an a priori on the limit. We believe that this is Gaussian, so we are going to use the Stein's method for Gaussian distribution. If we believe this is not Gaussian, then we have to use other tools. Okay, so in general, the intuition we have is that when we deal we deal with a short memory situation, we expect Gaussian fluctuations, and in the long memory case, we expect non-Gaussian fluctuations. Okay, and so this is the intuition forged over the 40 previous years by many works on this. Okay, so but I would like to show you that there are a lot of situations where it is not the case, and not only not corresponding to the critical case here, really in the case where we have a real long memory. So when you are in this case, when beta is strictly less than d over r, there are many situations where you can get Gaussian fluctuations. So I would like to go against this intuition. And for this, I will change my point of view. I will use the spectral, my spectral glasses to look at the problem. And so I will introduce a spectral central limit theorem, which is a new part in my title when I said old and new. Okay, so for this, I will assume, make a further assumption on B, which is also a natural assumption in many situations, that B is not only stationary, but it is also isotropic. Okay, so you will understand why I am assuming this in a minute, because it will allow me to introduce some important quantities related to B. Okay, but first let's see what happens. So let's see what we can say using that my B is stationary. So here I'm not, for the moment, I am not looking at isotropy. I'm just looking at the stationary property of B. Since it is stationary, so we know that, so it was the definition in our Gaussian context that the covariance of B only depends on X minus Y. So I can apply Bochner theorem. No, I can apply Bochner theorem, and it gives me, so it provides the existence of a finite measure G G on RD, which is called the spectral measure of B. Spectral measure of B. And it is defined so that so your function C of X can be represented as a Fourier transform of G, basically. So it is integral over RD of exponentials and the scalar product between X and lambda G d lambda. And so this is my entry door. This gives me access to the Fourier analysis argument. Okay, so I have this representation of C, so which defines my spectral measure. Okay, now let me go a bit further by also taking into account that my B now is also isotropic. So isotropy of B. Okay, so if I do this, there is another result I can apply, which is Schoenberg's theorem, which will give me a representation of the radial part of C. So, okay, so to say that, okay, well, let me write. So the function, I can define a function, so a so-called function mu of S, which is the integral for lambda bigger than S of G d lambda. So the G, the spectral measure of B. This function is, okay, so this is obvious that it is increasing in S. It is also bounded because G is a bounded measure. And so it defines a finite measure on R plus. Finite measure on R plus, called the, we can call it the isotropic spectral measure, because it only depends on the norm of lambda, isotropic spectral measure. And so we have, by the Schoenberg theorem, that rho of R, so what is rho? It is the function so that C of X is rho of norm of X, because if I assume that my B is isotropic, C not only depend on X, but only on the norm of X. Okay, so this defines my function rho. And we have this representation. We can write it like integral from 0 to infinity of BDRS mu ds. So the mu that I already introduced here, but here I see it like a measure, where the BD of u is related, is the scaled Bessel function of first kind of order d over 2 minus 1. So we have a certain constant, which is not important. Then we have u minus d over 2 minus 1. And then we have g d over 2 minus 1 of u, where this function g, this is the Bessel function of first kind. Okay, so I have this representation. I will use it in a minute, and I will go back to it when I need. And now I am in a position to state my spectral CLT. So the result I got with the Leonard domain. Okay. So what is this? What does this result say? So we are going first to assume that R is even, because in order to see the phenomenon I want to describe, we need R to be even. So you can think of R is 2, even if I will give other situations of interest, but for my meta remarks, so you can think of R is 2. Okay, now we set MTR, which is integral from 0 to t of rho u power r u d minus 1 du, which is more or less, up to multiplicative constant, the same quantity than the integral for x, the norm of x bounded by t of cx power r dx. So just to see why this is true is just polar coordinates, because you remember that c of x is rho of norm of x. Okay, so I can apply polar coordinates to this integral, and I will get this integral. So this part coming from the Jacobian, right? Now, what is R? You remember that this R here was the Hermit rank of my function phi, and this C is the covariance of B. And this quantity, which is here, we are in the case, or I would like to find to give you a statement in the case where C is not R integrable, because if so, meaning that if this quantity has a limit when t goes to infinity, I will be back in the setting of Breuer-Major, and so it's not interesting. Here I don't have absolute values because I assume that R is even, so I don't care about absolute values. So here I would like to look at situations when this guy goes to infinity, when t goes to infinity, but I have Gaussian fluctuations. So I will add to Breuer-Major situations when you can have that C is not R integrable. So we are in the long memory case, but still we have Gaussian fluctuation. Okay, my main assumption to get this is the following. So assume that my spectral isotropic spectral measure mu that I defined in the previous slide has a negative moment of order d over r. So let's assume that this is finite. So this is a condition only at 0, because at infinity, even if I put infinity, mu is a finite measure, so it is always satisfied at infinity. So this condition is a condition at 0. So let me assume that I have this, which is a spectral condition, hence the name here. Then, under this sole condition and the fact that MTR is regularly bounded, I get that the variance of YT is approximately equal. So when I write this, I mean F is a big O of J and J is a big O of F. So there are two constants, so that F and J are sandwiched by this constant. Okay. Then the variance of YT will be TD times MTR. So this is something that diverges to infinity quicker than T over D, because MTR, I am in a situation where when it goes to infinity. But still, YT divided by the variance of YT converge in law to the standard Gaussian. So it means that basically here I am describing a family of situations where you have Gaussian fluctuations, but C is not R integrable and can be actually very far from being R integrable. Okay, the best I think is to illustrate this on an example, and you will understand from this example the phenomenon I am describing. Okay, so let me now give you an illustrating example, which is a very rich example, because from it you can understand a lot of nice phenomenon arising in this context, and it will be even more developed by Giovanni in his talk. So this example is around the so-called Berry random wave model, which is a popular subject of interest now. There are a lot of talks around it. And as you will see, it will be discussed in Giovanni's talk. Berry random wave model, we can think of it as a universal Gaussian field, which emerges as the local scaling limit of a number of random fields on two-dimensional manifolds. Okay, so I'm not getting, so Giovanni will explain this in his talk, but so just to say that this is not just a particular example, this is really a universal object. Okay, and what is this object? So here I will fix the dimension to be exactly 2, and for mu, I will take the Dirac mass at 1 for my isotropic spectral measure. So what does it mean? More concretely, it means that if here I take the Dirac mass at 1, it is like my rho of R is nothing but in the case where D equals 2. So I should say this. So here, if you look, when D equals 2, this power is 0. So you don't have this mu, this U, and this is 0 as well. So you get G0 of U. And so if here I take mu is Dirac mass at 1, it remains only this G0 of U up to some constant. Right? So it means that when I choose delta, mu is delta 1, it corresponds to the model where the covariance function of my Gaussian field is given. So as covariance given by expectation of Bx, By, it is so G0, the Bessel function of order 0 of first kind, x minus 1, norm of x minus 1. Okay, so this is the definition of the Berry random wave model. So once again, Giovanni will explain where it comes and will give you a lot of information about this process in his talk. Here, what is interesting to note is first, because mu is delta 1, here, sorry, so mu is delta 1. So this condition here is automatically satisfied because there is no, you are not touching zero. So it is clear that this quantity is finite for mu is delta 1. So we will get central limits theorem in this situation when D is 1 and R is even, because this condition, once again, is automatically satisfied. But on the other hand, if we look at what is in this situation, the function rho, so here rho of u, so this is the function G0 of u. No, maybe, sorry, I will keep at the level of C. So here, what I wanted to say is that, okay, so G0 of u, we know the asymptotic of this guy. So this is square root of 2 over pi u cosine u minus p over 4 plus the big O of 1 over u when u goes to infinity. So for instance, you can obtain this asymptotic in any books dealing with Bessel functions. So you see that G0 is like u power minus 1/2 at infinity. Okay, and so if we compare with the intuition we had, sorry, where is it? Here, the intuition we have here, I will explain that when for the value R is 2 and D is 2, we are in the long memory case, but we see Gaussian fluctuations. So let me be more precise. So now let me choose R even. R is 2, R is 4, and R is bigger than 6. And we will see in these three possible values for R, 3 different things. So in my spectral CLT, you have that the variance of YT is of order T power D MTR, where MTR is this quantity. So here I gave you the asymptotic of rho of u when u goes to infinity. So I have everything I need to compute MTR, the asymptotic of MTR, and to see what my spectral CLT is saying. So if I do this, I can make easily the calculation, and I will get that the variance of YT is like, so I have the T power D, so T square. And what is MTR when R is 2? So let me assume that R is 2 here. It is integral from 0 to T, rho u square. So I have R here, and here I have D minus 1. So because D is 2, it's u du. Okay, and what is this guy? So rho of u, and once again, it is like 1 over square root of u. It's like u power minus 1/2. And so in this case, in the case of the very random wave, here this guy, so it's like 1 over u. You multiply by u, it's like 1, and so you get the t, and so you have something that behaves like t cubed. In the case where r is 4, you get t square rho u power 4 u du. So rho of u is still 1 over square root of u. So 2 power 4, it is 1 over u square. You multiply by u, it's 1 over u. And you integrate, it gives you a logarithm. So you have t square logarithm of t. So this is for r is 4. And when r is bigger than 6, you get that you have rho of u power r u du. And now rho of u is 1 over square root of u. You take power r, so what is inside the integral is integrable. So the integral does not give anything, and so you get that this is t squared. So we see that for all these values of r, we don't have the same phenomenon. And strangely, and Giovanni will speak about this in his talk, the rate, we have this rate t squared log t. So this rate corresponds to the critical case in Breuer-Major and Breuer-Major. We have the normal rate, which should be T cube if R is 2, but we will see that we have some cancellation phenomenon in the talk by Giovanni, so we will explain this. So for the moment, it's not clear, but just to, okay, so what I wanted to say was that, so here we are in the critical case in Breuer-Major. So we are exactly in the case where you pass from Breuer-Major to Breuer-Major. So the fact that we have Gaussian fluctuation and a logarithm is something which is well known by specialists and by experts in the field. Here we are in the case where we are in, when we have Breuer-Major that can be applied. So we don't need our spectral CLT, even if we get the same conclusion from our CLT. But this part here is not explained, the first part is not explained by the Breuer-Major or the Breuer-Major case. So here we get a variance of order T cube, but still Gaussian fluctuations. And we can imagine a lot of results of this kind by playing with our spectral CLT. Okay, just to say, so here I decided to illustrate the use of this theorem, but I did not say anything about the proof. For the proof, okay, so I won't give you details because time is running, but let me just say that for the proof, we rely on the so-called Malin-Weinstein approach, which is an approach I developed with Giovanni something like 10 years ago now, even more. Which the idea behind was to use Stein's method to get to have an access to the fact that the limit we expect is Gaussian, and when you apply the so-called Stein's approach or Stein's lemma, it gives you a bound of this kind. So here, if you have f a random variable with mean 0, say, and variance 1. And you would like to compare its slope with the standard Gaussian for some distance. So here, this is the total variation distance. Then, so this is Stein's lemma. Then this quantity, this total variation distance can be shown to be bounded by the supremum over a class of function g of g prime of f minus expectation f g of f, where g here are functions which are bounded by square root of 2 over pi and which are Lipschitz of constant 2. And it turns out that, so this is not a symmetric statement, so I mean n disappeared in the right hand side, but the idea behind is that using Stein's lemma, if you want to prove that the law of f is close to the law of n, what you have to do is to prove that expectation of g prime of f is close to expectation of f g of f for g like in the supremum. And so, in order to do so, a natural tool is to try, for instance, to start from this term here and to apply, or to try to apply an integration by parts formula to make an expression that is comparable with this one. And it is exactly what we did, what we do in the Malin-Weinstein approach. We use the operators of Malin calculus and mainly the integration by parts we have on the Malin calculus to write that expectation of f g of f. So here this is the Malin calculus part. To write that this guy can be always written under minimal assumption on g and f, like expectation g prime of f time df and then minus dl minus 1 of f. Okay, and so what the message here is that we have an integration by parts, and now this equality, even if you are not specialist of Malin calculus, maybe this guy is not clear for you, but just you see that you have now an expression that allows you to compare this expectation of fg of f with this guy. And because we know that g prime is bounded by 2, we get that, so this will be my last word, we get that the total variation distance between f and n is less or equal than 2 expectation of 1 minus df minus dl minus 1 of f when you plug everything together and you bound g prime by 2. And now if you want to prove that f is close in distribution to the standard Gaussian, what you can do instead is to prove that df minus dl minus 1 of f is close to 1. And so you can apply concentration inequality tools, for instance, because you transfer your problem of proving that a variable concentrates around its expectation, because 1, if f has variance 1, is the expectation of df minus dl minus 1 of f. And so we have plenty of tools, and using these tools, we can prove our spectral CLT with a lot of works, of course. Okay, I think I stop here. Thank you very much. And if you have questions, of course, I'm happy to answer them.
Well, thank you very much for this nice talk. So first, some round of applause, maybe.
Thank you.
And maybe now a round of questions. So if you have some, feel free to unmute or to write it in the chat.
Sorry, what is L? L capital is the last formula.
L is a generator of the Ornstein-Uhlenbeck semigroup. Okay.
And what is G? G capital?
D is the Malérand derivative. Yes, I was quick on this part. So here I am really using the classical notation of Malérand calculus. It would be another talk to explain you about this formula and consequences, but mainly, so D is a Malérand derivative. L is the generator of the Ornstein-Uhlenbeck semigroup, and L minus 1 is its pseudo inverse.
Thank you.
So I have two questions, if I might. So first question is, you said about this intuition when beta is small, right? But if you put beta equal to 0, you get 1. So if I understand correct, you get just one constant Gaussian variable, which gives you Gaussian limit in a trivial way. So I just wanted to ask if you explore the kind of connection to this, because somehow it seems to me like the limit case. And in particular, if one takes a look at these limits as Hermit random variables, do they in some sense converge to Gaussian if you let beta go to 0? So that would be one question.
Yeah, okay. So maybe I answer this question already. Of course, here beta, when I say this is strictly between 0 and d over r, you could have the envy to take beta is 0, but then it's not clear that C is covariant. So I mean, C must be a covariant. So in general, you have the covariance.
I mean, it is a covariance. It's constant equal to 1.
Yeah, but okay. So but if I take the L of x, okay. But it gives you a strange Gaussian process, right?
Yeah, you just a trivial example. I just want to ask if there's
yeah, I don't know, but certainly in this case, parameters of the Hermit random variable, yeah, maybe there is, I don't know. So I am not able to answer this question because I never have think about this already, but if you have Hermit random variables, so basically these are multiple integrals with special kernels, and we have all the tools in order to prove that they converge to a standard Gaussian. So this is the fourth moment theorem of Nourdin and Pecati. So I cannot tell you because I never did the calculation, but if you let the Hurst index of the Hermit random variable to be close to 0, or to be close to what corresponds to beta is 0, which is would be more precise, certainly it converges to Gaussian. But okay, I never tried, so I cannot say.
Okay, thanks. So I have a second question, because if I understand correctly, at this moment you formulate your results in a case of F, which is just it's just one-dimensional setting, because I'm not sure how to exactly formulate this, but in Breuer wave model.
Yeah. Okay. I see what you mean.
You have several fields that contribute to the function.
So here you would like to consider it is the integral of phi bx, comma cx, comma dx. Okay, and several Gaussian.
If you can generalize to that, or if you believe that you can generalize to that.
To generalize this as a general context like this looks quite difficult, because then you have to expand phi in Hermit polynomials, but in a multivariate setting. So already
but I'm asking more like, if you already say took as your variable just say this collection of Hermit polynomials, right? But you would have products of different, say, H2 of one field and H2 of another field, and that inside of the integral. I just focus on that. If you could,
okay, I understand
your result.
I understand the problem, but for me it's quite difficult. So I don't know if, of course, for instance, Giovanni in his talk will speak about the YT, which has the form you mentioned. So which depends on B, but also on the gradient of B. And because B is Gaussian and the variance is 1, the Bx for fixed x, Bx and the gradient of Bx are independent. And so in this case, you can say something, but this is not at the general level, I would say. But okay, so maybe it's feasible, I don't know. So we are at the very beginning of this thing. So indeed, any idea or questions that could extend this is interesting, but for the moment I cannot tell you.
Okay, thank you very much.
Yeah, I see questions in the chat.
Yeah, perfect. You can answer them.
Yeah, yeah. So it's right in the beginning. The criticality is discussed for parameter beta, but later it is discussed for parameter R. No, I was speaking about criticality for beta. Where is it here? Oops. This was not what I wanted to do. Sorry. Here, so what I mean by critical case is when beta is exactly D over R. Right? For R, it's a Hermit rank, so we don't speak about criticality because it's R is an integer. But here, criticality is just here. So I say that this is not covered when beta is D over R. This is not covered by my summary. But in a lot of cases, we know that in this case, we have Gaussian fluctuations. And what happens in general is that you must multiply by a logarithmic correction so that you still get Gaussian fluctuations. Yeah, I'm not sure I replied to the question. I saw another question. Can we apply this machinery to some non-Gaussian stationary isotropic fields P? So this is a good question. And my answer is a bit the same. So I mean, this is at the very beginning of the story. So for the moment, I cannot tell you. But the point is that the Mallier-Stein approach indeed has been developed. So originally it has been developed. I developed it with Giovanni on the Venus space. So in the Gaussian world for functionals of a Gaussian process. But then it has been extended by many people. In other contexts, and notably Poisson processes or Levy processes, and there are many works on this on stochastic geometry. So we have plenty of tools. The main difference, I would say, is that here at the very end, I spoke about this integration by parts. So when you are not in a Gaussian context, in general, you don't have an exact integration by parts. You have the first beginning plus a reminder. And so the reminder, the fact is that the reminder, you have it in the end in your bound on the total variation distance. And so it means that if you want to prove that f is close to n, in the case where you are not in the Gaussian context, you not only have to prove that this guy is close to 0, but also the reminder. So they are extra work, but why not? So I mean, there is no reason why it should not work. So.
Perhaps I
So
should say, Ivan,
yeah.
because I asked this question, that if phi is linear, then there is nothing to do essentially for a Gaussian case. But so the question for a non-Gaussian field would probably, can it be reduced in some cases to knowing something extra about the field, like mixing or rapid? So you would expect. You would expect a central limit theorem that depends only on the covariance function of the stationary field, and then you have the nonlinearity introduced by F, if that makes sense, by comparison somehow with the original.
Yeah, I understand. So exactly as you say, so is my Hermit rank is 1. So basically, and I consider that my Hermit expansion, I have a dominant term, which is R is 1. So it is already Gaussian. So to check that it converges to something Gaussian is just a question of checking that the covariance converges, right? Yeah. So if you start with something which is not Gaussian, so if your phi is still linear, but the B is not Gaussian, then you have something more to do. And again, so we have setting and context in which we can do this in many other situations that is Gaussian for Gaussian functionals, and certainly here we could do the same in other contexts. But I cannot tell you now that it works in this because but there is no obstruction. So basically, it should work also in others.
Sorry, for what behavior of correlations your theorem is stronger than Major theorem?
Exactly in the situation that I described in the very random wave model. In the case, for instance, and so if you are interested in this, Giovanni would speak about this precise model in his talk, but exactly in this case here, when I have R equal 2, so Hermit rank is 2, I am in dimension 2, and my Gaussian field is a very random wave model. In this case, I am in a situation where I cannot apply Breuer-Major theorem, and not only because I am in the critical case, but because I'm really far from Breuer-Major theorem. I am more than closer to the Breuer-Major theorem, but still we have a Gaussian fluctuation in the limit. So this precise situation, which is quite simple here, but which is exactly a situation where we have a long memory, but Gaussian fluctuations.
Mm-hmm. Thank you.
Which one? Yeah.
Okay. So I suggest maybe we stop the question session here, even though I know there is still one in the chat and maybe others in your head, because we will need to switch to Giovanni shortly. But before doing so, we can make a second round of applause for Ivan.
Thank you.
And now we have a 1 minute break or 2 minutes maybe. And meanwhile, we can make the technical switch to Giovanni. And if
we share my screen on my iPad, hoping that it works as it worked before.
It seems to be loading. It works. Very good.
Now we move pages. Do you see the pages moving?
It moves smoothly, so no problem at all.
That's fantastic. Great. I'll just wait for your signal.
Sure.
Start my presentation.
Bastien, do we make 2 videos or one?